Section 19, paired differences. Okay, so when it comes to comparing two variables, there's various ways that you can do it. One of the ways we talked about in sections 14 and 15, you can take a simple random sample from each of two different populations independently. 40 people from New York, 100 people from Massachusetts, and compare their proportions or averages, as we did. And it's important to remember in that particular scenario, number one, that the samples can be of different sizes because they're independent. The New Yorkers that you happen to pick has no bearing on the people from Massachusetts that you happen to pick. Also, another thing you want to remember is that they've got to be the same kind of thing. You know, proportion of left-handed people versus proportion of left-handed people. Average height in feet versus average height in feet. Remember, things can only be compared, added, subtracted, which is less, which is greater, if they're the same kind of thing. Gallons, degrees Fahrenheit, whatever. There's another way in which we can compare two very different kinds of variables, which we'll talk about in section 16 and 17, correlation and linear regression. You can talk about how the heights of the trees compare to their ages and so forth. But a third way that you can compare two variables is to take what our book likes to call two dependent samples, but it probably would be more to the point to say that it's one sample of pairs. So that we have an example of a this and that, another example of a this and that, a third example of a this and that, and so on for a total of n examples. Picking a sample of n pairs. So suppose we have a population of numbers. Suppose we have a population of numbers, pairs of numbers. For instance, you could talk about heights of husband and heights of wives for all possible husband-wives. Or you could talk about cure time for a drug and cure time for the placebo. Ideal times if you were to give the drug or the placebo to everybody, or times for 100 pairs. Likewise, you could talk about heart rate with caffeine versus heart rate with caffeine. You could talk about how that compares for all people, or you could look at 100 people and get an example of each and go from there, samples. Reaction time when hungry, reaction time when not hungry, if you're going through a maze or solving a puzzle or something. Height of father, height of son. You could talk about all possible father-son pairs, or you could talk about sample, 100 examples of father-son pairs. Time to catch a falling object with your right hand, time to catch a falling object with your left hand. Same idea. You could talk about how those times compare for all possible people, or for 100 people that you happen to pick. Likewise, for all possible people, or for all possible students, or for a sample of students, you could talk about the grade before they study versus the grade after they study. In general, these are very good for before-after studies, when you want to see whether something is actually having an effect. The ideal example here would be the placebo one. Cure time with the drug versus cure time with no drug. You can see whether the drug is actually, under ideal circumstances, having an effect. So the idea here is that you have a sample of pairs, which is being used in one sense or another to approximate the population of pairs. The way we're going to do this is differences. So we're going to actually subtract the one variable from the other. Doesn't matter which you subtract from the other as long as you're consistent about it. Height of husband minus height of wife. Height of husband minus height of wife. Conceptually, or for the 100 pairs that you happen to look at, and so on and so on. Height of father minus height of son for the 100 pairs you happen to look at, or the ideal difference between height of father and height of son, and so forth and so on. So the idea here is, in this problem type, we're talking about, does the average difference in the sample provide evidence that there is a difference on average in the population? In other words, the average of the sample differences is approximating the average of the population differences. The statistic is the average difference in the sample. The parameter is the average difference in the population. In particular, is there one or is it 0? So we could do this in all of our usual ways: confidence intervals, hypothesis tests, but we're going to stick to hypothesis tests. And in fact, we're going to stick to a particular type of hypothesis test. So let's organize our facts. From the population of all possible pairs, we take a simple random sample of size n. That sample consists of so many pairs. One of these, one of those. Another one of these, another one of those. A third one of these, a fourth one of those. And so on and so on. Height of husband, height of wife number 1. Height of husband, height of wife number 2. And so on and so on. But unlike when we had two samples previously, here we have them in pairs. For each example, the one goes with the other. Also, they're the same kind of thing, height in feet, height in feet. Cure time in seconds, cure time in seconds. And so on and so on and so on. Grade, grade. Call it percent out of 100 number. So, because they are the same kind of thing, we can subtract them. Remember, it doesn't make any sense to do feet minus gallons. In order to subtract things, they've got to be the same kind of thing. So you can do this either way you like. We'll stick to first minus second because it's a little easier. But as we've seen in the past, it really doesn't matter which variable you call which. So for the sake of argument, whatever the first thing happens to be minus whatever the second thing happens to be. So we will do that for all n of our matched pairs. Example number 1, height of husband minus height of wife. Example number 2, height of husband minus height of wife. Example number 3 from the sample, height of husband minus height of wife. So from the sample we get n numbers, 100 pairs, 100 numbers, which represent differences between the one variable and the other. And then we take those 100 examples of a D, of a difference, and we average them together. D bar. Notice the fact, apart from the fact that we're calling it D to represent the fact that it was a difference, this is exactly what we do in sections 12, 13, and in particular 18. So D bar is the mean of the observed differences. The average difference in husband and wife for the husbands and wives you looked at. The average difference in height of father and height of son, the one minus the other, for the 50 father-son combos you looked at, and so forth and so on and so on. So let's organize our facts. D bar is the mean of the observed differences. 100 pairs, 100 numbers when you subtract them, average those numbers together. Mu of D represents then conceptually the mean difference from all possible pairs. The average height difference between all husband-wife combos, or all possible husband-wife combos. The average height difference in all father-son combos. The average grade difference for all possible students before studying, after studying, and so forth and so on and so on. So from the sample, we have those n numbers. We find their average, section 2, add them up, divide by n, and their standard deviation, the standard deviation of however many differences you have. As always, computing S from section 2 is a little bit tedious. In theory, you do the work. In practice, we'll try to start at the point where those have already been computed for us to cut down on the tedium of it. So from the sample, we have the statistics D bar, the mean difference in the sample, and S sub D, the standard deviation of the differences in the sample. And then from the population, the thing we're trying to approximate, the mean difference for all possible pairs. So there's lots of theories you could test, but we'll stick to the obvious one. We will test the theory that on average in the population there is no difference. There is a difference of 0. And we will test that against the 3 standard alternatives. The difference is less than 0, the difference is greater than 0, the difference is not 0. As always, the grammar of the question will tell you whether it's one-sided or two-sided, and the question you're not asking is not plausible, you know? For instance, what I'm trying to say is that, as always, the two-sided question is always plausible, and exactly one of these is plausible. For instance, if the sample suggests that husbands tend to be tall, if the sample could possibly suggest that husbands tend to be taller than wives, then it certainly doesn't suggest that wives tend to be taller than husbands. If the sample could plausibly suggest, if there's a prima facie case, that maybe the sample could suggest that on average grades will be higher after you study, then that sample is not going to suggest the reverse, and so on and so on. If the sample could plausibly suggest that fathers tend to be shorter than sons, then the sample certainly doesn't suggest the reverse. As always, the trend is going one way or the other. That's not the question. The question is whether the direction matters. And as always, you make the call whether it's a one-sided alternative, only one of these is plausible in any problem, or a two-sided alternative from the grammar of the question. So there is how we organize our facts. If d bar is reasonably close to 0, then it's plausible that the population average difference is 0. If d bar is very negative, then it suggests that the population average difference is negative. If d bar is very positive, then it suggests that the population average difference is very positive. And if d bar is very far away from 0, then it suggests that the population average difference is not 0. Same old, exactly what we did in section 18, and in a broader sense, section 13, using the sample average to test theories about the population average. More like section 18, of course, because you'll notice we're not talking about any sigmas here. We're not talking at any point about the standard deviation of the differences from the population. That's kind of abstract and not the kind of thing you could ever possibly know. So we're going to stick to using S, which means we'll be using T procedures. Apart from that, it's exactly like section 18 with the following differences. Number one, we're labeling things a bit differently. We're talking about d bar instead of x bar. We're talking about s sub d instead of s. We're talking about mu of d instead of mu. We just want to remind ourselves at all time that these things started life as differences. But numerically, they're the same thing we were doing in section 18. The other difference from what we were talking about in section 18 and previously is that we're specifically testing the theory of 0 rather than other numbers. We could test other theories, but all I'm going to do is test the theory of 0. Is it plausible that on average there is no difference in the population? Versus, do we have evidence that the difference in the population is negative or positive or just plain not 0? In the red, you have the usual disclaimers for when this is considered good, but the bottom line is we don't have any practical alternatives. It's important to remember, again, that this is exactly what we did in section 18 once you get up and running. In fact, once you get to the point where you've got these D numbers, these N numbers, these N examples of a D, these 100 differences, from there, it's exactly what we were doing in section 18, only the notations are a little different, and the fact that this happens to be 0 changes our formulas a bit. But the test statistic plays out exactly the same way it always does in theory. In theory, things are normally distributed. So our test statistic is statistic minus theory about parameter divided by standard deviation of statistic. Well, the mean of the standard deviation of the sample mean is sigma over the square root of n. So we have the following adaptations. First of all, we're using d bar and s of d instead of x bar and s, simply to remind ourselves that we're talking about differences. Second of all, our theory is 0, so that's going to simplify our formula a bit. And third of all, because we are using the sample standard deviation to approximate that unknown sigma, again, that makes it a t rather than a z. So our test statistic formula, just based on an adaptation of what we did in section 18 with slightly different symbols, is t equals d bar minus 0 over s of d over the square root of n. That's the order of operations. And because you don't really have any real subtraction on top, you can flip and multiply. So if you're thinking about how it stacks up compared to the previous formulas, again, the logic is the closest thing we've got to statistic minus theory about parameter divided by standard deviation of statistic. But if you want to just cut to the chase and simplify the double fraction a bit, we compute t by doing d bar times the square root of n over s of d. And remember, our sample consists of n differences, 100 pairs, 100 numbers, 100 differences. So 99 degrees of freedom, or in general, n minus 1. So n minus 1, where n is the number of pairs, the number of differences in the sample. 50 pairs, 49 degrees of freedom. 18 pairs, 17 degrees of freedom, and so on and so on. From there, it's just like we did in the previous section. In fact, once you get the paired business out of the way at the start of the problem, it is literally just an example of a section 18 problem with slightly different symbols. Use the t-table, choose the appropriate one or two tail header, one tail header if you're doing one of these, two tail header if you're doing one of these, to estimate, to ballpark, the corresponding p-value. We have the same limitations with our available charts that we did before. Same old t-chart, same old ballparking method. And then the usual conclusion of the test. If the p-value is less than the level they give you, say 5%, then you reject H0 and find evidence of HA. You reject the theory that there is no difference in the population. You find evidence of however that parses out. If the p-value is not less than the level, 5%, whatever, then you don't reject H0 and you have no evidence of HA. Note the typo there. Of course, we've done this several times already, so you should catch the typo there. I have no way of getting back to my office to make those changes, but I'll try to remember to put something up online about it. If the p-value is higher than 5% or whatever level you're using, then you do not reject H0 and you do not have evidence of HA. Typo. State your conclusion in the context of the question. Yes, we have evidence that on average fathers tend to be taller than sons, whatever. And this just summarizes what I've said a couple of times now. Note that these problem types, despite some different notations, are simply an example of the test in the previous section, where the sample and population numbers happen to be differences. Only the interpretation changes, but the numerical part in the middle and the mathematical conclusions you draw, it's all the same stuff. We just have a slightly different origin story for the n numbers that we're using. They happen to be differences. So there's the theory of paired difference hypothesis tests. In the second part, I'll do a couple of examples.